Great, so slides should be coming through. So thank you very much for inviting me to give this talk. I'm really happy to be here. As introduced, I'm going to be talking about provably faster gradient descent, and the title gives away the trick for how we're going to get faster results. We're going to take longer steps. So that's maybe pretty simple. So some disclaimers before diving into the algorithms and the math. So this work is really recent. I put it on archive on, I think, July 12th. It's August 11th now, so that's less than a month, just barely. So this is the first time I'm talking about this work. I apologize if there are issues in the slides or anything is unclear. So please feel free to ask questions throughout or put them in the chat. I'm happy to be interrupted and clarify things kind of where I go off the rails. Disclaimer number 2, this work has kind of had an unbelievable track of public attention. When I first put this online and tweeted about it, it got like 500,000 impressions, and this morning an article in Quanta showed up. So I think there are lots of eyes on this work, which means it will probably become outdated quickly. I hope it becomes outdated quickly and we find even better ways to do what I'm going to talk about. So don't expect me to give kind of conclusive end of the story things here. I'm hoping there is much more to come, and this attention will rapidly get us to even better results. Okay, disclaimers out of the way. The overall outline for what I want to talk about here today. First, I'm going to preview the results. So I'll give you the good stuff up front. We're going to get better smooth convex optimization guarantees. Then we'll kind of go back in time and I'll justify why we should expect this, because I don't think these results come out of nowhere. There's really prior work that leads this path quite well. To get into the proof machinery, it ends up being pretty thorny to give these better guarantees. So I needed to resort to some computer-aided proofs, a bunch of semi-definite programming. We'll get there. And then finally, the last kind of step is to figure out what long steps we actually should take once we have our proof machinery built. And that involved a bunch of heuristics and brute force searching. That's really where I think the improvements in the future will come, because what I ended up doing for the last leg of this work is a lot of heuristics. So there'll be plenty of future directions at the end, and I'm excited to see what comes next. All right, so let's preview the results. We're looking at L-smooth convex optimization, and I just want to use gradient descent. So kind of the most basic setting. We're looking to minimize maybe that red function. And our variables, although I can only draw in one dimension, live in Rn for some generic n. So by L-smooth, what I mean is we have an L-Lipschitz continuous gradient. So when the function turns quickly, there's a bound on how quickly those corners can actually be turning around. As well, I want to assume, kind of for ease throughout, that there is actually a minimizer and that we have some bound on how far our initialization can be from it. This number d puts an upper bound on, given your initial objective value, how far off from the minimizer you can be. So we'll take that kind of as the basic setting. And then gradient descent. I'm sure you've all seen this method before. Gradient descent takes step sizes h1 through h, however many steps you're going to run. And at each step, you linearize the objective. That's coming up with this blue linearization at your current iterate. And you move some amount downhill in the steepest descent kind of idea. So our step size is given here by hk over L. So the over L is normalizing with respect to how smooth we are. So you can roughly disregard that and just think about one smooth optimization. So then hk is really our freedom in picking how far we move. If you set hk small, you're going to get good steps down that are kind of conservative, but give you some profit, seeking the minimum. And if you set hk large, you risk shooting over past the minimum onto the other side of the shape. So we want to come up with some good strategy for balancing out the h's to eventually converge down to the bottom quite well. So the classic theory is on the conservative side. If you pick your favorite textbook, the best guarantees I could find in them are of the form, always take step size 1. And if you always take step size 1, then your objective gap after t steps will look like LD squared over 2t plus 1. But that's the the best rate that you can get from just all step size 1. And why do you choose h equals 1? And that's a good motivating question. And there's a good answer, right? So why have we taken step size 1 in the past? Well, the answer is to look at this descent lemma, the kind of classic result. If you take what L smooth means, kind of integrate up your Lipschitz gradient, there's a quadratic upper bound on your objective, and you'll have descent if you take steps between 0 and 2. If you take a whole step of length 2, you might have gone to the other side of this quadratic upper bound and not decreased at all. So anything between 0 and 2 gives a decrease. And if you want the best decrease from this quadratic upper bound, that's h equals 1. And really that is the best one-step decrease you can get. If you want your next iteration to be as good as possible, h equals 1 will give you that. So the moral of this talk is that style of thinking is too short-sighted. If we just think about getting my next iteration to get as much descent as possible, then you're doing a greedy algorithm. At every step, you're trying to take what's best right now. But our metric at the end of the algorithm is how good is the final solution. We don't care about the intermediate iterates. They're not what you return back to your boss. We're just looking for the final step to be good. So the way we're going to approach this, getting away from this greedy one-step kind of analysis, we want to be able to look at longer horizons. Say, okay, if I'm going to take my next 10 steps, I want to be better 10 steps down the road. What's the best thing I can do to have that profit eventually? I don't need my next step to be the greedy best step. We can take a longer horizon. So I think this moral is running throughout the talk and should apply to more algorithms than gradient descent. Everything I'll talk about here in math today is about gradient descent, but I really think this moral can and should be taken to more algorithms outside gradient descent. Okay, so let's get an example of what I'm talking about. So the simplest thing that I can do to break this intuition is just to alternate between 2 step sizes. So instead of always taking steps of size 1, getting the best descent out of just one operation, instead, my proposal would be you should alternate between 2.9 and 1.5. So your first step is a little bit too long, then your next step is within what the descent lemma can talk about. Then you go too long again, and then descent again. The guarantee that I'll be able to prove for this is that after t steps, alternating through these, you'll have objective value like LD squared over 2.2t plus some lower order terms. So on my previous slide, the textbook guarantee was 2t, and so we're 10% faster here. We've replaced 2 with 2.2. That's a small gain, but I would argue that it's a proportionally small change to the algorithm. Right? We didn't change what the method does. We kind of got a free lunch here. Just do exactly the same computation you had before. Instead of hard coding 1, hard code these numbers, and it's better. Right? There's a plus 1 over t squared here. That captures some lower order terms. Don't worry about those. We're going to see them later. They're not that scary. So they're really lesser order terms. So to get some intuition for how you would argue something like this, I've sketched 2 possible one-dimensional scenarios we could find ourselves in. To prove a theorem, we're going to have to think about every possible function. But to get some intuition, I just have 2 examples. You could think about a problem that's just a slow slope down on the objective. Right? The only reason that this problem is hard is because the slope is small. So it'll take a long time to walk along it. Or you could have an example with a quick U-turn. So optimal is pretty nearby and you're risking overshooting. So if we go run my proposal, on the slow slope down, I'm pretty happy. Right? We took longer steps than normal, so we're making a quicker pace down the slope. We did 2.9 and then we did 1.5. I think everyone can agree long steps are good there. The U-turn is kind of surprisingly good. The 2.9 will overshoot. Maybe it went uphill or downhill, since I don't have a guarantee that the arrow will go down. But after 2.9 overshooting, 1.5 looks really good. 1.5 will bring me back to about the middle. It depends on the slope on the left and right side here. But the 1.5 will just about cut in half what I did on 2.9 and get me right back in the middle. So I'm quite happy with the final result. If I instead plot what conservative policy would do, it makes steady progress on both iterations. So on the slow slope, 2 steps can't even match what the 2.9 did from the other method. On the U-turn, these are conservative steps. They're never going to overshoot. So they're going to march down the side here. But at the end of the day, in my doodle, purple came out better than blue. Even though after 1 step, purple wasn't better, after 2 steps, purple was. And so the kind of thing we're going to show is that when you look at the worst case over any function for purple, it's going to have a better worst case than the conservative classic policy. So if we can show that it's always going to be better in the worst case, then we'll get faster convergence out of using purple instead of blue. All right, so that's the basic kind of picture for the intuition we're going to be breaking and what we're replacing it with. So we can go more than just alternating between 2 step sizes. That's just the motivating example there. So we could take a whole pattern of steps and repeatedly apply that. So if you have step sizes h1 through ht minus 1, and we're going to do those in the first t steps, and then we're going to repeat and go through the pattern again. And the next t steps uses these and so on. The result I'm going to prove is that if h is straightforward, so that's a property that will be telling us that we have good control over the worst case. If h is this kind of well-controlled problem, then our objective gap will go down at a rate that's like LD squared over the average length of step inside h times t. So we want to get our average step large. The 2.2 on the previous slide came because 2.2 is the average of 1.9 and 1.5. So that's where that comes from. All right, so pulling this out of the paper, this is a small table, but in computer-aided fashion, I produced a bunch of patterns with increasingly good average step size that gets us increasingly good coefficients. So here it goes, steps, a pattern of length 2, a pattern of length 3, 7, 15. Okay, let's just pull out the best one. So here's my biggest pattern. If I had my computer burn harder, I'm sure I could have found a better, longer pattern, but this already got pretty expensive. So if you are going to do 127 steps every cycle, my proposal is instead of doing 127 steps of length 1, all conservatively making some progress, you'd be better off if you took steps 1.4, then 2, then 1.4, then 3.9. Okay, the pattern goes on. The 8th position is a 7.2. It gets pretty large. And then eventually our biggest step comes in the 64th location, which says to do 370, which is an obscene number, right? 1 to 2, 0 to 2 is what we can guarantee descent for. So this is saying go almost 200 times longer than we could guarantee as descent. And yet this pattern is designed so that that ends up being a stable good thing. After you do
Professor
that
Grimmer, so there is one question, is that if the order of the pattern matters or not?
The order matters deeply. So we'll see some examples of that later. But the order is really critical. So I don't have a great theoretical foundation for why this order is the best. I'll give some sketch in the kind of end of the talk heuristically on how I built this. But if you permute the order here, things will fall apart. So it's really, really sensitive. So this long step of 370 will exactly be handled by all these other steps. So if we overshot on this 370, it's like the purple picture I had before. If you overshoot on the 370, the other steps are going to be able to recover excellently. We'll have overshot and the other steps will zero us back in. So no matter what happens, even if that step is locally bad, globally we're going to be better off than if we were always conservative. If you took the average of all the numbers here, you get about 5.8. And so this pattern is 3 times faster in the worst case than the classic approach of always step size 1. All right, so
another quick question, if that's all right. So with h equals 1, is h equals 1 not a straightforward pattern, or is the upper bound that we saw somehow not an optimal upper bound?
Yeah, so I suspect the upper bounds I'm proving here might not be optimal. For h equals 1, there's a custom proof. So the proof that gets 2 instead of 1 there uses some extra knowledge that my proofs aren't able to use. So it might be possible to power up my proofs, or it might be something special about h equals 1 that you get 2 here instead of 1, right? Because the pattern of all ones has average length 1. I don't see how to do with my theory.
So another question
just
from
gets you-
Professor Freud. Yeah, so let me just repeat it. So are the derived sizes really just using one decimal place? So you are showing
Yes.
1.4.
So,
okay.
So I brute forced on one decimal place. There is a whole lot of repeated numbers in here. I had to do a lot of things to save computationally. So some of the reasons why there's repeated numbers is to cut down on the degrees of freedom I have. My brute force search in finding these was searching out to one decimal place. For some of these, I could get at some analytic formulas, but not in a way that's rigorously satisfying. So here we've brute force shown, a lower bound on what's possible by demonstrating these are possible, but I don't claim that these numbers are the analytic limit that you could push to. All right, any other questions here? Okay, I have one numeric in the whole slide. So this is primarily a theory talk, but I took these patterns and ran them on a very simple setting. So if you look at least squares problems, randomly generate data A and B, minimize AX minus B squared. That's on the left, or minimize AX minus B squared plus a 2 norm squared, which makes the problem quite strongly convex. On the right, we see that the improvement from that table carries over immediately. So as you do the longer patterns and get the better rates I claimed, the method just marches down and performs better as you go. In the strongly convex case, the lines are linear. We're getting linear convergence at a faster and faster rate. So that gives some numerical demonstration. I'm not going to have more numerical demonstration in this talk. I'm excited to see those in the future, but for now I have the theoretical motivation, which will hopefully lead to the better numerics in the future.
One question from Anand Sahai. If these are random problems, are the plots the median or a representative random problem?
They are, this is a representative one sample. So the plot looks identical if I sample a lot. There is a whole lot of regularity that comes out of random problems. If you look at like the spectrum of A, as you draw random problems, the spectrum of A doesn't really change, or rather A transpose A. It's very low variance. So the plots ended up looking almost identical. Yeah, so here it's not sampling a lot of problems. It wouldn't be too meaningful in my mind to sample a lot of random problems. If we're going to do a good numerical survey, we should give up on random problems and go use a lot of actual data set problems. Yes, this is just one representative sample. But yeah, I've run it dozens of times and it always looks like this.
And also, like, yeah, if anyone has any question, like, you can of course put it on the chat, but you can also ask directly. No problem with that.
Yeah, absolutely.
I have a question about your the sequence you had for T. So is that for a very specific problem, or does it believe that is 3 times faster for any problem?
Its worst case bound
Right.
is 3 times better. So that doesn't mean for every instance it will be 3 times better.
Yeah, but it's on average.
You could set up an instance where step size 1 gets it in one go, and this will end up oscillating around. But what I'm guaranteeing is that in the worst case, this has a 3 times better worst case, if that makes sense.
Yeah.
Right, but that doesn't mean on every problem instance this will always be better.
And so you would
want
to change it
on average.
So that'd be something to change. Let's say if you knew the problem or you knew there's a certain type of problem, you would be changing this H pattern basically. But this T equals 127 is for this specific type of, or is it just like you did a lot of problems? Yeah.
No, so this is over the worst case of all smooth and convex problems. So
okay, I see.
Right, so this is the problem class here is really quite general. So this is looking at the worst case over anything smooth and convex. Great, I love the questions. So that's the preview of the results with no justification for why, really. So now I can justify more rigorously where this comes from and why you should believe these crazy patterns. All right, so why to expect this? The machine that kind of underlies my thinking here is this performance estimation problem setup, which is really about finding the worst case problem instance given a fixed algorithm. So you could imagine you fix a whole lot of parameters about gradient descent. So if you tell me exactly how many iterations you're going to run, you tell me you're going to run 7 steps, tell me exactly the step sizes that you're going to use, tell me the problem dimension, the smoothness, distance to optimal, initial gap. If you specified all of those, you could imagine sending someone out to go find the worst problem instance, given this fixed iteration bound, fixed policy on everything. Right? So you could go about coming up with the worst case problem. Naively, if you write down what I'm asking, you'll get an infinite dimensional optimization problem. Right? What's the worst case problem? Well, maximize the final objective gap, so f of xt minus f of x star. And you do that maximization over every possible objective. So f has to be convex, f has to be smooth, bounded distance to optimal, bounded initial gap. X star should be optimal. So X star should have 0 gradient. Since we're convex, that's necessary and sufficient. And the algorithm should run in this agreed upon prescribed way. Right? So given that you've fixed all of those parameters, we could think about this infinite dimensional problem to come up with the worst instance. Now, infinite dimensional problems are usually not very useful in practice. We typically can't solve them. So the fantastic result that kind of builds up this performance estimation tool is from Drury and Tabboul, who showed that you can discretize that problem. So instead of worrying about the function and gradients of it everywhere, well, we could just care about the iterates instead. If you just looked at the points xk that are iterates 0 through t, and also I'm going to let k equal star as a way to talk about optimal, but we can look at the function value and gradient at every iterate and at optimal, and just enforce smoothness and convexity at those points. So you could let ft be a scalar equal to the function value at xt, gt would be a vector for the gradient at xt, and then we can write down what looks like a relaxation of our previous infinite dimensional problem, maximize over any way you set the function values and gradients at our points, the final gap, ft minus f star, subject to this first constraint is implied by smoothness and convexity. If you ignore the term at the end, this looks a lot like convexity. It says your function value at I is bigger than your value at j plus the linearization. And then smoothness gives you this extra correction. So this is implied by smoothness and convexity. So this is a relaxation of the previous infinite dimensional problem. It turns out that this isn't just a relaxation, it's actually a reformulation. So this is an equality here. Taylor, Hendricks, and Gilner proved that, which is an amazing result. Right? So that gives us some real reason to believe there's power in this machine. Since this is equal, it means we can solve this finite problem and actually know the worst problem instance. Now, this problem is still hard to solve. As written here, this is a non-convex optimization problem. Everything in here is quadratic, so that's good news. But we have this product here between g and x, and products between variables quickly make things non-convex. So this is a non-convex constrained quadratic program. The standard trick, if you ever run into a non-convex quadratic problem, is to reformulate it or relax it as an SDP. So we can go through that. So that's exactly the way this performance estimation tool has been developed. You could relax this into a semi-definite program. So here, our variables are this f and g. There's a bunch of problem data to make this problem be equivalent to the previous one. Those are these matrices A, B, and C that show up in here. They're not too critical for the intuition for what's going on, so I want to avoid defining them at the moment. But you could relax that non-convex quadratic problem as a semi-definite program here with, again, finite dimension. So this thing is very solvable. It's actually equality here as well. So it's a relaxation in general. You can get it to be equality so long as the problem dimension you're looking at is big enough. It needs to be bigger than the number of iterations plus 2. So assuming you're interested in high dimensional problems, you can also make this an equality. Again, that's thanks to Taylor, Hendricks, and Gilner. Okay, now we're really cooking with something, right? We can take this infinite dimensional find the worst problem and reformulate it with equality, if we look in high dimension, to be a finite sized semi-definite program. Semi-definite programs, we have great solvers, right? So this is now looking really good. We can compute the worst case in a fixed scenario, right? So we still had to fix the scenario. We had to say, we're going to do 7 steps and then be done. But given that you fixed the scenario, you can try to find what step sizes give us the best worst case, right? That's a mini-max problem, but we know that we can evaluate the inner max. We can turn it into this SDP. So that's exactly the kind of approach that Shuvo took. So he developed in this paper, which is now in math programming, a branch and bound method capable of solving that mini-max problem. Right? So they applied their setup with, say, doing 5 iterations. If you were going to do exactly 5 steps and then stop, the best step sizes to take, globally optimal, numerically found by their method, are about 1.5, 2, 1.5, 3.5, 1.5, something like that. They ran their method for 10 steps, 25 steps, 50 steps, and really you start seeing big steps come out. Right, so these don't give a theorem per se, they're just telling you the best on a fixed horizon. But if you're going to do 50 steps, this pattern will give you the best final guarantee. Somewhere right around the middle, there's a step that's about like 37. So we start getting some of these wacky big numbers, like my theorems have, out of this numerical search. Right, so if we put this side by side with my kind of patterns, there's really a lot of similarity. That comes in large part because I was inspired to this problem by this work. And so seeing these numerically found patterns up to length 50, that's where the procedure they had kind of sputtered out. Up to length 50, you get these crazy patterns that claim to give better performance. We should be able to give a theorem like that. And so the first place where I started building intuition for where these patterns come from was staring at these tables in their paper. So they have a big step in the middle and some bigger steps on the side, but mostly small steps. And that, at least in spirit, carried over to my table. Now, the particular patterns here aren't actually straightforward, this property that I need for my theory. So we can't directly port their patterns over, but the spirit of them is really our first indication towards these patterns I have. All right, so that gives us a numerical justification that there is something here, we should go finding theory. We have a numerical case for it. There are some prior works that give probably good results. So not just numerical justifications. The biggest line of this work comes from thinking about strongly convex quadratic minimization. So we're strengthening convexity, and instead of smooth, we're saying it's a quadratic. So there's actually just a constant Hessian. Not a bounded Hessian like smoothness gives you, but constant. The kind of hallmark result in this area is David Young's result 70 years ago, which said if you're minimizing a quadratic like this, what you should do is take steps given by 1 over the roots of this Chebyshev polynomial. So I've taken this figure here from this Agarwal paper. These roots are given by taking these evenly placed points along the top half of the ball, dropping them down, and the best step sizes, according to Young, are 1 over these. And these subsequent works looked at the order that you take these step sizes and found that the best way to order these steps in this strongly convex quadratic case was this fractal kind of crazy pattern here on the right. But if you take these steps in this kind of order, what you're guaranteed is the same thing as a accelerated momentum method. So you get the same improvement from condition number to square root of condition number that we get from things like Nesterov's acceleration. And so doing this pattern, really pays dividends. It gets gradient descent to be as good as momentum methods. So that theory is, has now been explored for quite a while. And there's lots of work being done more recently on bounding the stability of that. So one more paper here doing strongly convex quadratic problems. Grudjund et al. Gave optimal cyclic kind of patterns if you were doing a heavy ball method. So a different kind of acceleration. And that, very strangely to me, needed a kind of bimodal spectrum. So not only are you strongly convex, so your spectrum is positive, but your spectrum also splits into two disjoint intervals that are far away from each other. So there are some interesting things looking at other algorithms with cyclic kind of step size policies as well, but that gets beyond what we have time for today. So then the next kind of related work is looking at strongly convex smooth problems. So instead of forcing it to be a quadratic with a constant Hessian, let the Hessian change. So OMAC recently showed similar bimodal structure in the Hessian can speed up optimization in smooth problems. Right? So doing a similar kind of cyclic pattern, you can really get a benefit if that Hessian structure continues. Maybe the most related thing to this talk, Jason Altschuler, in his master's thesis 5 years ago, looked at optimizing in a similar way that we do, the contraction factor you get for smooth, strongly convex problems. Looking at optimizing the constant for how much you shrink towards optimal at each step. So when I get into the proof details, I'll sketch what he did. It's really got the same theme here. So that's a great work. All right, then the last thing to kind of point at, I'm not a neural networks person, but there are several examples in the non-convex, smooth kind of neural network world where learning rate schedules have a kind of cyclic pattern. So they either are some restarted pattern where you decay the step over time and then restart and jump it back up, or these works by Smith gave kind of triangular patterns that increase for a while, then decrease and alternate back and forth. Those have found numerical success. Now, that's not a kind of area that my theory today will apply to, but this gives some motivation towards the spirit of what they're doing, and maybe we'll give some justification a few papers down the line. So, okay, that's some reasons to expect that we should be able to give better theory than the textbook kind of always take step size one conservative bound. So if there are any questions about kind of the prior theory, it's another good place to stop. All right, great. Then we'll dive into the fun stuff. So we need some computer-aided proofs to actually get a way to analyze those big sequences that I had before. So to get a theorem, really what I need is something inductive, right? Because I don't want to apply to just a finite schedule, just 50 steps and done. I want some way I can argue that after you've run T steps for any big T, we have good convergence. So something inductive needs to come about. And what this master's thesis did is it looked at getting the best contraction factor. So here I have a performance estimation problem similar to what I wrote before that works for mu strongly convex problems. So we're not just doing convex, but we're going to see what's the farthest from optimal that you can be at the end of this pattern, given you started distance d out. So a good inductive proof would be if we could show that the result, your distance from optimal after a pattern, is smaller than the original distance by some amount 1 minus tau. Right? That would be kind of the type of thing we're angling at. So you could write this down and say, I want the best contraction factor. Right? That would amount to solving, you want to minimize over all h's, the worst case distance from optimal. So find the best contraction factor. And what Jason did in his thesis, he found the best contraction factor actually solving this problem, for t equals 1 and 2, and then an example for t equals 3. So if you're going to alternate 2 steps, you can go to his thesis and find what are the best 2 steps to alternate to get the best contraction factor. This is a finite problem, if you set t equal 2, the outer minimization is 2-dimensional, and the inner problem, you can write it down as an SDP in the same PEP way. So it's a finite problem, a gnarly mini-max problem, but a finite one. And you could work it out and get the best pattern for some t. All right, so I'm looking at just regular convex problems. I just want to do smooth and convex. So we're not going to get a contraction argument. There are lower bounds for smooth convex that say the best you can do is sublinear. So we need some different angle to try and get a handle on what the worst case behavior will be for smooth convex problems. And so the way that I kind of eventually got at this, I wanted to have the worst case be something that we could really get our hands on. And the nicest worst case in my mind is this slow slope down, right? If the reason that gradient descent is slow is just because you're walking down a long hill, that's pretty easy to understand. Up in high dimensional problems, I'd be worried about all sorts of other things. It'd be really nice if the worst case was this slow slope. And so that's what I want to focus on. And I want to make it more formal so it's not just a doodle. So one worst case you could think about is the function looks linear all the way down towards optimal. And if you want, you could put a little smooth curve out at the end there. You could smooth that out so it's a smooth function. But here I've just written it as piecewise linear. It shoots straight down linearly and then flattens off at optimal. So I'm interested in when is this slow slope actually the worst case? Despite all the high dimensional possibilities, when is this the worst case problem? Well, we can calculate what happens here. So as some notation, I'll let delta k's denote the objective gap at k steps. dk will give me the distance to optimal after k steps. And what happens with this example is, provided you pick delta small enough, after t steps, your objective gap looks like the initial gap minus a term that's quadratic in the initial gap. If you set delta bigger, we're actually just going to hit optimal, and then it zeroes out. So this only works for delta small. But as long as your initial gap is small, this method has a really simple formula for what the worst case is. So in my mind, this method is, or this example is really the simplest possible example. We're just having gradient descent move in a straight line down this slope. So that's what I want to define as my useful property. So a step size pattern H is straightforward if this example bounds its worst case. So it only works for delta small. So I want to say that there's some big delta such that every objective gap between 0 and LD squared big delta has this property that the worst case, this P function we defined before, the worst case is at most the original gap minus a quadratic in the original gap. Right? So the reason this is an upper bound is because my example here isn't actually smooth since I made it piecewise linear. So the worst case might not even be this bad, because this is a non-smooth problem. Maybe this is extra bad. But provided that this is a bound on the worst case, things can never be worse than walking down this slow slope. I'll say that the step size pattern is straightforward, and we're going to have a good time in analysis. Things are going to be easy for these patterns. So convergence rates kind of follow right away from the definitions I've given here. So we get an induction right out of this. What we have here, if you're straightforward, every time you apply the pattern, the objective gap goes down based on the square of your initial gap. Right? So the objective gap after s+1 applications of the pattern is less than the original gap minus a quadratic in the original gap, under the assumption that you started within the region where this applies. Your initial gap was low enough. But you can solve that recurrence. It's just linear minus quadratic. If you solve that out, you get a formula for an upper bound on it. And that formula is on the order LD squared over average of HT, plus a constant in the bottom. So as long as you start well enough, straightforwardness immediately gives the type of guarantee that I've claimed in my original table back in the first part of the talk. So we can get rid of this good enough assumption. It's annoying to have to say that you started good enough. It makes things a little bit uglier, but okay, that'll be fine. So more generally, if you're straightforward, we have that for delta st small enough, you get the recurrence we had before. And if you're above that region, you can show that it has to be contracting towards that region. So you have a linear decay towards this level. So quickly the method is going to hit this level capital delta, and then we'll have the convergence we had before. And if you solve that piecewise recurrence I have there, it just gives you that there's an initial linear phase up to some iteration s bar. And after that, you then get the rate that I've claimed here. So that's the kind of stuff that I'm hiding in that big O 1 over t squared. It hides this initial phase. So we're hiding the piecewise linear phase, and we're hiding these constants that you're dividing by that depend on this s bar and this delta. So those are all suppressed into the lower order terms, but the leading term of convergence is LD squared over average of HT. So that's the simpler way to state the results. All right, then the last convergence result that comes for free from this, if we bring back strong convexity, right? We built a machinery that didn't need strong convexity here. If we do assume that you're strongly convex, we get back the contraction kind of results. So if you're straightforward and strongly convex, then your objective gap will contract at every iteration. So your initial gap will shrink by something that depends on the condition number, L by mu, improved by the total length of steps we took at every iteration, once you're good enough, and we have the same early phase. And so you can carry this through and you get a linear rate that improves based on the total length of our steps whenever you're strongly convex. So we haven't lost strong convexity as a result by going into this more general convex setting. Those still all follow. So now we can kind of give our overall strategy. What I want to do is come up with straightforward patterns that have large steps on average, right? Because if I can get the average step to be large, that's directly getting me a better theorem. You know, I'm getting to improve the denominator. So our strategy will be to propose a pattern, prove that it's straightforward, and then we can conclude the kind of rates we have here. All right, so we've already shown that you can do this last one, right? If we can justify that these patterns are straightforward, right away we have our convergence guarantee. So next I want to tackle number 2. How do we prove that something is straightforward? Right, so straightforwardness is saying, in the worst case, you're never worse than that piecewise linear function. How would I prove a bound like that over all possible functions? Okay, so how to prove straightforwardness? First, I'm going to give a sketch, and then we'll go through some actual mechanics to build a proof. But I want to show that no matter what smooth convex function f you have, if your initial gap is less than delta, the final gap will be less than delta minus this quadratic in delta. I'd like to prove that inequality for every delta, no matter what function f you're looking at. So how could you prove something like that? Well, in one way too simple of proof would be to just pick weights and add up the inequalities that we already know. Right, so I know that the distance squared to optimal minus d squared is some negative number or non-positive. So I could add that inequality times some weight v of delta. Another inequality that we know is that the initial gap is less than little delta. So initial gap minus little delta is again non-positive. We could add it up with some weight w of delta. Then we have all these smooth convex inequalities. We could add those up with weight lambda ij of delta. And if you pick the weights carefully, you could hope that there's some way to add together the inequalities we know to get this to simplify to what we want to show. Right, and that would be a really nice proof if we could just directly add up the given inequalities and conclude the target. So we, in general, can't do that, but this is going to work for all the patterns that we have in my table that I've claimed. So the good choices that are going to end up working as we more rigorously build a proof in this style will be that you should pick this v of delta weight to look like delta squared, w of delta is 1 minus delta, and lambda of delta should be some linear function, although it gets pretty hairy. Those will end up being choices that make this type of proof sketch actually go through. Now, coming up with these things is hard. You have to pick these magic multipliers. But this ends up being the form of proof you could give to show that a certain pattern is straightforward. So now the game is going to be to figure out these multipliers. Find v, w, and lambda with this property, and then we know we're straightforward. Okay, so let's take a step back and build somewhat just pulling magic out. So what we know so far, we have this performance estimation STP. So if you look at this P of delta, which is our worst case over any problem instance with initial gap at most delta, we know that we can upper bound that by this semi-definite program. Now it's equality most of the time, but we can upper bound it by a semi-definite program. You can upper bound a maximization problem by its dual. So we can go ahead and compute the dual problem. So the worst case gap is upper bounded by the minimum of this dual optimization problem. And actually Taylor continued and showed that this one's also usually equality. We usually have strong duality here. You just need to avoid some degenerate cases like taking step size equal to 0. But assuming you avoid degenerate cases, it would actually be equality all the way, but we just need the inequality. So we can upper bound our worst case by a minimization problem, which is really great because any feasible solution to this minimization problem gives us an upper bound as well. So just demonstrating feasible solutions for this problem will suffice to give upper bounds on PL. And you can see if you look in this dual problem, the names of these variables look like the strategy I was just outlining. Right, so V is my dual multiplier for the distance constraint, W is the dual multiplier for the objective gap constraint, and lambdas are the multipliers for the smoothness and convexity constraints. So that magic argument is really an argument looking at this dual problem. So okay, what are our ingredients we have? We want to show that the final objective gap is at most delta minus the term squared in delta. And we know that any feasible solution to this problem will give us an upper bound of the form we're looking for. So I numerically went and solved this minimization problem a lot, right, for the patterns I'm interested in, and went looking for patterns in the choice of V and W. And a really nice pattern shows up if you go numerically solve this. The optimal solution usually has V and delta about equal to these formulas. Right, so V should be chosen to look like delta squared. W should be chosen 1 minus delta. And since I'm numerically solving this SDP, I could change all the parameters slightly and see how it changed to figure out what functions these are. But if you check, V and W have the great property that if you evaluate the objective at my proposed values of V and W, you get exactly the right-hand side we're looking for. Right, so all we need to do then is show that it's possible to get a feasible solution with these choices of V and W. So if I can justify there's a way to pick lambda that completes this thing being feasible, V and W will give me my objective and give me the upper bound that we're looking for. All right, so that's formalized as this lemma here. If you can show that for every setting of delta, this set is non-empty, this set is essentially the lambdas that complete feasibility for this problem I have here. So if you can show that for every delta, there is a way to complete the feasibility certificate given by V and W, then we'll know that our bound holds for every delta, and we have straightforwardness, we get our convergence rates, woo. Okay, there's still a problem here. Doing this for every delta is hard, right? There's infinitely many deltas. So I still would need to do some analytical argument to justify that this set is non-empty for this whole interval of settings delta. Okay, so that's still too much. Okay, so we need some trick to handle all of those in one move. So here's our lemma from before. What would be really nice is if there was a line of solutions that work. So if as you change delta, I don't need to generate a new certificate. What if it just steadily changes? And the way that this certificate moves as I change delta is just some linear function. It's initially little lambda, and then as you increase delta, add on delta copies of gamma. If you go and write down what that means pretty quickly, you'll see that checking, is there a linear certificate that works for this interval, is just another semi-definite program. Right? So you can write that down and you get a theorem. So if you can show that for some bound on the initial value, it's big delta, this set is non-empty. This is a set of all the lambda gammas, and it's some semi-definite program. But if these are true, these end up being exactly the conditions you need to have a line of solutions that work for any way you pick little delta. So if I give you a feasible solution to this set, you can generate an interval of solutions to use in the lemma. The lemma will get you straightforwardness. Straightforwardness gets us rates. And again, we have better theory. So the problem can now be reduced all the way down to finding a single feasible element of this set. So if we can do that, then we get our rates. And that's something I can hand off to my computer. Right? I can ask my computer, go find a feasible solution to this semi-definite program. So it can really be automated away, the way of proving that H is straightforward. Okay, so that gives us a proof technique. We can now just ask our computer to prove it. It will come up with a certificate lambda and gamma and return that to us. And then we know we have a better rate. So the thing we're missing is, how do you pick those steps H? Right? Given that you've selected your steps, I can, in computer automated fashion, ask, is there an inductive argument that works like I want? So we're going to get at this with some heuristics. Sadly, I don't know the optimal way to pick the step sizes. I'm working on that, but for now, I don't know the optimal way to pick them. So we need to propose step size patterns. But once you've proposed your pattern, we know how to prove it straightforward. Our computer can do that. Then we get to conclude our rate. We've already proven that. So how do we propose patterns? Well, let's start from small things. I want to look at patterns of length 2. The ideal thing would be to go about solving, maximize the average length element in H, subject to this strange constraint that big spectral set I had before is non-empty. Right? So that set depends in a non-trivial way on your choice of H. But if that set is non-empty, we know we're straightforward and we know the proof works. So for patterns of length 2, we can just go look at where is that true. Right? So here I solved, a few thousand SDPs to check what configurations for our steps H1 and H2. So that's one of the typos in these slides that I was sure would show up. That should be H0 and H1. I start counting from 0. So with your steps H0 and H1, this region is the region that has this spectral set non-empty. And so it's the region where we're straightforward and where we get my convergence rates. So if you take the classic setup, the classic thing would be step size 1, 1. That's this dot here. What the descent lemma tells you can do is everything inside the box. Inside the box, you have descent on each step. What we can prove with our machinery is that everything in the blue region has descent after 2 steps. So in just 1 step, you can only be in the red box. But if you look ahead 2 steps, you get these extra regions of possibilities. And if you go to find what the largest patterns are, there are these 2 points. They're both equally good. They're approaching 3, 1.5 or 1.53. So those aren't actually in there. I'm only able to show this set for a fixed choice of delta. But as you take this number delta to 0, we would approach having those points be in the set. So those are not themselves straightforward patterns, but our optimal patterns approach them. So theorem, my claim is that anything a little bit short of that is straightforward, and so we get a rate. So if you have a pattern, take a step a little bit smaller than 3, and then a step 1.5. My claim is that that's always straightforward, and so you get these better rates for alternating 2. Okay, I want to prove this theorem, and the proof is a little bit lackluster. All right, so that's my proof. The proof is, here is a value of lambda and gamma that are feasible to that STP. So any way you pick beta, these values will be feasible to that STP. And so all the previous theorems give us our rate. Right? These lambda and gamma tell you a line of solutions to the original PEP problem. We have feasible solutions for all the original PEP problems. Those give us straightforwardness. Straightforwardness gives us rates, and we're done. So the proof really is just then come up with certificates. The computer can write these proofs for us. So that's the best thing you can do using my machinery for length 2 patterns. If you're going to go through this straightforward tool, that's as good as you're going to do. All right, so we can go to length 3, try to get some intuition for where these are coming from. So this set is the set of all patterns H0, H1, H2 that are straightforward. Right, so here I've labeled the same kind of points. So the best thing is up here at the top. I have a 3D printed copy of this. Okay.
Wow.
You can either look at my slide or you can look at me with my my model. But okay, so this thing is a non-convex region, right? This thing is not easy to operate. So the best thing is this point up here. That's where you set the middle step large. It's set almost approaching 5 and 1.5 for the other options. And you have 2 local maxima. If you went to solve this numerically, you'd find yourself getting clustered in either of these local maxima. One of them is when you set the first step size big. If you really wanted your first step to be the biggest, you end up suboptimal here. So that gives some evidence that this thing is not safe to perturb, right? If you move the 5 to be in the first location, it doesn't work. You have a much worse solution if you want your first step to be the biggest. And same if you want the last step to be the biggest. It's a much worse region. This thing is actually symmetric. So if you mirror this and do the steps in reverse order, it's the same set. I don't have a proof that that symmetry holds in general. It doesn't hold for even length patterns, but for odd length patterns, I think that might be true, that you can always reverse it. But okay, that's just conjecture. I'd love it if one of you proved that. But this gives us some structure about what we should be doing in general. So we should have this mirror symmetry that seems to work, and we should have the biggest step in the middle. That's at least what works for patterns of length 3. So we could take this and try to generalize some more. So after 3, the next one I want to do is 7. It got really expensive to try and search for high-dimensional solutions to these non-convex.
I think there is one question.
Can I ask a question?
Yeah.
So I'm a bit confused. I mean, aren't you going to do the same thing over and over again? So why is the middle, like in the middle, so A, B, C, 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 A, B, C? Isn't it, like, why would it matter if you started with B, A, C versus, you see, I think you see my question?
Yeah, so I do. There are a dozen great intuitions here. So that's a great question. The thing that's breaking that symmetry, because that's a symmetry that we should be able to respect, is that when we do this straightforward definition, I guess here we'll do, when I define straightforward, I specified a place where we're going to check. I'm going to check the objective value after t steps. I'm not going to check the objective value at any intermediate place. So to prove that this inequality is true, this inequality doesn't have to be true if you shift all the indices by 1. I'm just claiming that it's true at iteration 0, 3, 6, 9. So in particular, when I have those really big steps, when you take a step of length 5 or length 370, perhaps the worst place for you to check, have we gotten enough descent, would be immediately following that huge step. Because at least I believe that huge step is going to overshoot. And it'd be a terrible time to come in and check our descent for induction right after the big step. So in fact, what we're getting with this symmetry is we're checking descent, we're checking if this lemma is true, as far away from the big step as possible. Right? So when I go to prove this, straightforwardness for this pattern of length 3 is saying that we have good descent in the objective value after 1.55, 1.5, and then check descent. So we're only ever going to check descent in between the 1.5s. We're not going to check, have we gotten enough descent after or before the 5? So it's an artifact of when we check for descent in the inductive argument. Because certainly the iterates would be the same, but the theorem likes having our place we do our inductive check be very structured. You could come up with a corollary that does some off by one correction if you really wanted to analyze a different pattern. But the straightforward property I've defined here wouldn't be true if you cycled everything a little bit. You'd be checking at a bad place. Hopefully that makes at least enough sense to tide you over. Okay. All right, so I want to do longer and longer patterns, and I stopped being able to visualize things. So based on this kind of belief that things should be symmetric, and also based on these prior works, I can go look at Chauveau's paper, and he found the best thing to do if you're doing a fixed pattern. And that's to put a big step in the middle. And at least when I squint at these things, they look kind of fractally. It looks like left and right of the big step are similar. They're not exactly, but they look similar. So my guess for a structure, based on previous works and based on the symmetries that I see here, is that we should do steps that look like ABA, C, ABA. Do some big step C in the middle and repeat some pattern on the left and right. So I can tell my computer to go searching over any choice of A, B, and C and find the best choices of A, B, and C numerically. So as Rob asked at the start, okay, I just said search over a discretization of size 0.1. But I can have my computer churn at this and figure out what choices of A, B, and C have this descent lemma, this straightforward dishold. It found what the biggest setting was. So I took these floating point numbers. They alone don't give me a proof, right? These are lambda and gamma, but they're just in floating point arithmetic. They don't actually have the PSD properties that I want. The equalities don't actually hold perfectly true. So then you can give that to some exact arithmetic engine. So I handed those to Mathematica and asked it come up with rational numbers nearby that exactly solve my problem. And okay, so it comes up with some monstrosity because these were just ugly floating point numbers. If you want to find nearby rationals, you'll get ugly rationals, but it's an exact arithmetic proof. So these tiny numbers here are all the lambdas and gammas that would show my claim in that table does have that spectral set be non-empty, and so everything runs backwards. All right, so we can keep doing this. I want to keep the dimension low for searching so I can efficiently check a lot. So for 15, repeat the previous pattern, put a big one in the middle, repeat the previous pattern. 31, so on. So we can get really big patterns now with very few parameters. So the time to solve these grows pretty poorly. The SDPs here, for the largest one, 127, this SDP has something like 127 squared variables that all have 127 by 127 matrices associated with them. So the problem size kind of looks like 127 to the 4. So rather terrible to directly put this in to MOSIC to solve. So that's around where my computer burned out. If we went bigger, if we went longer, I'm sure we would get better patterns than I have here. This is more a first paper showing what's possible rather than getting numerically the very best. All right, so that generates this whole table. We get 127 based on taking this structure, which just gives us 7 parameters to figure out, and then doing a discretization search over the grid. Ask my computer, is there a proof for this selection? And find the best thing in the grid. All right, so from this table, I have a conjecture. I think we can get big O improvements. So as you go down this table, the best thing I found from my discretization would grow by about 0.6 per doubling. So each time I went and searched for a pattern that was better and twice as long, my average went up by 0.6. That points to there being patterns that grow logarithmically. There might be other structures because I've searched a very narrow band of what's possible, just trying to do the things that look like the prior numerically optimal. You might be able to do better than growing logarithmically, but my table points towards a logarithmic growth. If you could come up with formulas that are straightforward H's growing like this, you would probably get a 1 over t log t rate for gradient descent. If you did better than this, I'd expect you get t to a power, but it doesn't look like this is running out of steam as I numerically push farther and farther. So I really believe that 1 or 2 papers down the line, we're going to beat this 1 over t. I believe that's coming. Okay, so go ahead, yeah.
I have an observation about those numbers, the big jumps that are in the middle. I don't know, it would be interesting. I mean, it's hard to do because it's so computationally expensive, but to go further, because it looks like the big number increases by about 2.25 every time. So from 92.7 to 72.3, it's a little less accurate, it's 2.44. Then from 72.3 to 164, it becomes about 2.29. And then 164 to 370 is 2.256.
Right.
So if that pattern continues, there might be a way to find these t steps just to know what it is already.
Right. I believe one of the, okay, so the next bunch of slides I have are all future directions. I think I like the way you're thinking. Figuring out either asymptotic bounds on how these change or directly analytic formulas for what the best choices are should give us the way to actually prove something like this, right? Because either asymptotic bounds or exact formulas would give you a way to prove something like this conjecture. If these guys are actually growing like 2.5, like multiples of 2.5, I think that would beat my conjecture here. Because if the middle guy looks like 2.5 to a power, but the total length of the sequence is growing like 2 to a power, I think that disconnect would grow exponentially. So I think that if they grow like 2.5 to the t, I think you would beat my conjecture and do even better. That would be great. So I don't know if these guys are growing like 2.5 to the t asymptotically, as you run it out. If they shrink down towards being about t log t, or well, okay, yeah. I think there's hope in figuring out those patterns. I think that's the way forward. All right, so some of the future directions I see, I think I'm supposed to wrap up in the next 2 minutes. So, okay, I think there's lots of future directions here. This is really a first work on a topic rather than a conclusive work. So I'm sure that my patterns aren't optimal. One approach would be to directly try to solve a minimax problem over this. Right, what we want to do is, well, it's not quite a minimax problem anymore, but something similar to Chauveau's branch and bound method might work. If you wanted to maximize the average value in H, subject to this complicated constraint that says this STP is feasible. Right, so that is a multi-layered kind of optimization problem. You have to solve a problem to check the constraints. But if you could directly solve that problem, even just for small dimensions, that would likely give analytic formulas that might help us see the actual pattern, as things grow larger. So I think actually figuring out, the analytical best would be fantastic. Additionally, I think my proof technique here is likely not the best technique. Right? So this is the technique I could write theorems for. The thing you can prove is better than the thing you can't prove. But my convergence here just argues that the objective gap shrinks. You could make proofs that look at recursions on the distance to optimal, like the strongly convex smooth kind of previous works. The best thing is probably a mixture of the two. If you look at like Nesterov's accelerated method, it uses a hybrid kind of descent sequences that look at objective gap and distance. That might matter. You could make better inductions and figure out if there's some SCP that corresponds to proving a better induction. But this is the thing I can get a handle on. And it's good enough to advance the state of the art. Okay, then the last 2 slides I have here. I think that there's lots of extensions of this that should be explored and figure out if they're possible. I believe we can do adaptive types of methods. If you did some kind of backtracking, we don't actually know the number L to put here, But after you do a pattern, check if you got the kind of descent you expected. And if you don't like the descent that you got, back off on your guess at the smoothness constant, kind of classic backtracking line search. As well as there should be ways to explore how to generalize this to constraints. If we're doing projection or procs, Bregman methods, stochastic methods, monotone operators, and all the fun things in optimization. I'm sure it will apply to some of these. It will probably not apply to all of these. Figuring out which ones will take some work, but I think it'll be fun work. All right, so then the final thing, I think the moral of this talk, and what I'm hoping is the direction of research that can come after this, is beyond gradient descent. Because I think gradient descent is maybe the easiest algorithm to look at. But the moral overall is that we shouldn't do one-step analysis. And if we can find ways to look at longer horizons when we're building our guarantees in our theory, we'll get better guarantees for hopefully closer to actual performance. All right, so I suspect that kind of cyclic coordinate descent methods and other methods that are fundamentally cyclic might be the most natural, more complicated algorithm to take these over to. Additionally, I'm a big fan personally of gradient aggregating style methods, kind of dual methods. So those build up a memory over time as well. I suspect there are ways to take this to look at bundle methods or dual averaging. Okay, so my shameless plug here. I've written some papers on bundle methods and dual averaging that I like quite a bit. So if you want to look at dual ways of understanding methods, particularly this last paper here, I'm very happy about. So dual methods might be a very good place as well for this to go move towards. But with that, okay, thank you very much. I'll take any more questions.
Yeah, so if you have any question, please go ahead. Great talk, Professor Kramer.
Thank you.
So guys, if you have any question, please feel free to go ahead, and I will be stopping the recording now. Okay.